Hey there, and welcome. It's funny, our world can feel pretty random sometimes, right? But what if I told you there's a ton of order hidden just beneath the surface? Today, we're going to pull back the curtain and look at some super predictable patterns in numbers. Let's get right into it. Okay, let's start with a little puzzle. Look at this sequence. 2, 5, 8, 11. What's the 15th number going to be? Now, sure, you could sit there and just, count it out, but where's the fun in that? There's a much cooler, much faster way to solve this. And together, we're going to build the exact tool to do it.
So here's the plan. We're going to build a mathematical toolkit. First up, we'll figure out what this pattern is actually called. Then we'll get our hands on two awesome tools, one for jumping ahead in the sequence and another for adding it all up super fast. We'll even do a little detective work with them before we go looking for these patterns out in the wild. Sound good?
All right, first things first. Before we can start playing around with this pattern, we got to give it a name, We need to know the rules of the game. So, what are we actually looking at here?
So this type of pattern has a name. It's called an arithmetic progression, or, AP for short. And the magic word here is constant. It means the difference between the numbers is always the same. It's kind of like climbing a staircase where every single step is the exact same height. That perfect, predictable rhythm is what makes these things so useful.
And you know what's cool? Any AP, no matter how crazy it looks, really just boils down to two key ingredients. First, you've got A, which is just your starting number, and then you have D, which is the common difference, or the size of each step. So for our puzzle, A is 2 and D is 3. That's it. Simple, right? Okay, we've got the basics down. Now it's time to bust out our first power tool from the toolkit. This thing is a game changer. It's going to let us jump to any spot in the sequence without having to do all the boring stepping stones in between. And here it is, our predictor tool. Now don't let the letters scare you. A sub n is just a fancy way of saying the number we're looking for. And the formula is simple. You take your starting number, A, and you add your step size D a bunch of times. So how many times? Well, that's the n-1 part. And it makes total sense if you think about it, right? To get to the second number, you just take one step from the first. To get to the 15th number, you're going to take, you guessed it, 14 steps.
Okay, remember that puzzle from the beginning? Well, guess what? We now have everything we need to solve it. No more guesswork. Let's put this tool to work.
All right, let's break it down. First, what do we know? Our starting number, A, is 2. The step size, D, is 3. And the term we want is the 15th one, so n is 15. Perfect. Now we just plug those numbers right into our formula. We're going to take our starting number, 2, and add 14 steps, each one of size 3. A little bit of math later, and boom, 44. The 15th term is 44. See? No counting on our fingers, no writing out a long list. Just a super quick, clean answer. Now that is the power of having the right tool. Okay, that was pretty cool. But let's kick it up a notch, shall we? What happens when you don't know the starting number? What if all you have are a couple of clues from somewhere in the middle of the sequence? Well, my friend, it's time to put on our detective hats.
All right, here's the case. We have two clues. Clue number 1, the third term in some mysterious sequence is 11. Clue number 2, the seventh term is 23. Our mission, should we choose to accept it, is to figure out the two missing pieces, the starting number, A, and that all-important step size, D.
So, how do we solve this thing? Well, we use the only tool we have, our predictor formula. We're going to turn each clue into its own equation. For the third term, we know n is 3. For the seventh term, n is 7. And just like that, we've got two equations. And if you've got two equations and two unknowns, you can totally solve it. Okay, now watch this. This is the really slick part. If we just subtract that first equation from the second one, boof, the a's completely cancel each other out. They're gone, which leaves us with something super simple. 4d equals 12. Well, that means d has to be 3. And once we know the step size is 3, we can just pop that value back into one of the first equations, do a tiny bit of math, and find out that a is 5.
And there we have it. Case closed. We figured out the secret identity of our sequence. It starts at 5 and it goes up by 3 every single time.
All right, so we're pretty good at finding any single number in a sequence. But what if you wanted to add up a bunch of them? Like, say, the first 100 numbers. Ugh, that sounds awful, right? So much work. Well, lucky for us, it's time to grab our second power tool from the kit, the summation shortcut.
Check this out. This formula is our secret weapon for adding things up. The S just stands for sum. So S sub n means the sum of n numbers. It looks a little complicated, but it's basically a magic trick that lets you add up an entire sequence all at once, without having to do it one by one by one. It's a lifesaver. All right, time for a new challenge. We need to find the sum of the first 20 terms of this new sequence, 1, 4, 7, 10, and so on. I mean, you could write them all out and add them up, but why would you when we have this beautiful shortcut ready to go? Okay, you know the drill by now. Let's find our variables. A, the start, is 1. D, the step, is 3. And we want the sum of the first 20 terms, so n is 20. Now we just carefully plug everything into the formula. So we get 20 over 2. That's 10. And inside the brackets, let's see, we've got 2 plus 19 times 3, which comes out to 59. So the whole thing is just 10 times 59. And our grand total is 590. That's amazing. Seriously, just think for a second how long it would have taken to add all 20 of those numbers up by hand. This is exactly what I'm talking about. It's not about being a human calculator, it's about working smarter, not harder. So, we've built this awesome toolkit, right? But you might be thinking, okay, that's cool, but is this just math for math's sake? And the answer is a big fat no. Let's talk about where you can find these patterns in the real world, because I promise you, they are everywhere. Ever been to a stadium or a big theater? Think about this seating. Each row usually has a couple more seats than the one in front of it, right? That's an arithmetic progression. Or what about a savings plan where you decide to put away, say, $10 more each month than you did the last? Yep, that's an AP2. A job where you get the same raise every single year? You know it. These patterns are literally the blueprint for any kind of steady, predictable change. So today, we put 2 incredibly powerful formulas into our toolkit. But it's like William Paul Thurston said, math isn't really about the numbers and the formulas themselves. It's about understanding. And when you understand the pattern, suddenly you can predict what's coming next, you can figure out what happened before, and you can see the world just a little bit more clearly. So I want to leave you with a challenge. Start looking around. Where do you see these kinds of predictable patterns in your own life? Is it in how you train for a race, how you pay off a loan, or maybe even how many pages you read each day? The cool thing is, now you have the tools to not just notice these patterns, but to actually understand how they work. Thanks so much for hanging out with me today. And as always, stay curious.